Well, this is probably the last video that I'm going to create now related to angular momentum. There's been a couple before. First, just describing what angular momentum is and how you calculate it. The second, I looked at a couple of special examples where angular momentum is conserved and how you work through those. Now I want to deal with some specific kinds of collisions that tend to bother students a lot. These are also the kinds of collisions that AP tests love to put on there. And they're ones that I call combining linear momentum and angular momentum. And they kind of have this particular trait. You'll notice something either before or after the collision that just has straight line motion. You would tend to think of that as just a regular old linear momentum kind of a problem. This is like your track, your cart on your track, or a projectile maybe moving straight horizontally through the air. But then there's another element of the problem where things are turning, which makes you think angular momentum. So the trouble that students get into in these is they want to try to equate linear momentum and angular momentum as though they're the same thing. And they're not the same thing, although they're closely related. It's a lot like what students do with torque and force. Because every torque has some force associated with it, you want to think they're just the same thing. But they're not identical. You just have to know how to relate the two. So here on the screen, I've shown the first example. I'm going to do 3 of them, and they're all kind of similar, but I'll show you what's different about the outcome. I just imagine a little blob with some mass m, and what it's going to do is hit a stick with the same mass. The stick has a length L, and in the first situation, I've got the blob centered so that you just imagine, and maybe we're looking from a bird's eye point of view, so this would not be a blob like moving like a projectile. It's just moving straight horizontally, but when we look at it from above, it looks like this. And if it hits directly in the center, as I've got it shown here, then you might think, well, what's going to happen? Well, first of all, regular old conservation of momentum, linear momentum, still works here. So if these masses are the same, and this stick isn't moving initially, then all the momentum, the linear momentum, is contained here in the blob beforehand. But now, afterwards, it's going to be shared by the two masses together. And I'm not going to show all the work for this, but because the masses are identical, you're going to get half the speed afterwards that you had initially. So that's one thing. Certainly linear momentum is conserved here. Well, what about any angular momentum? Because it's hitting right in the center, this stick is going to have no tendency to spin around as a result of that collision. So we won't have any angular momentum either before nor after the collision. So this is just kind of a typical collision that we did like when we studied linear momentum. So let's look at the next example. What if instead of hitting right in the middle, we hit down here on one end? I've also added a pin. So I've pinned this thing down. So that means it's able to turn, but it cannot move forward. We no longer can say that linear momentum is conserved because this pin is going to be exerting an external force on the system. It's going to basically keep it from moving. So we would not expect any forward motion. But I think you can imagine that this thing is going to want to spin around as a result of this collision. So let's talk about what happens in a spin kind of a fashion. We have to be able to describe this now in terms of angular momentum. And even though this is moving straight, we can still calculate an angular momentum as long as we specify some rotation axis, which I think in this situation is pretty obvious. The rotation axis is going to be the pin. So if we give this thing an initial velocity vi and it's got a mass m, then here's how we describe its angular momentum about the pin. It's r crossed with p, and we want to examine that right at the moment just before it collides. So you got to picture this blob over here just about at the point below the pin. What that means is the r vector, I'll just draw it here in red, the r vector that we use to calculate the angular momentum is going to be straight down. The p vector is just going to be the mass times the velocity vector. That's straightforward. And so if we put in the magnitudes and we count for that 90-degree direction, all this is an r of half the length, L over 2, and m times VI. That is how we would express the angular momentum that the blob has just before the collision. Well, what about after the collision? Now we have this thing swinging around. And when we get into, let's say, masses like this, the stick, or we've done this with discs and spheres, balls, things like that, we don't try to describe it this way. We describe the angular momentum now, usually use a capital L for these kinds of objects, as I omega. It's just an easier form. It's totally equivalent to if we took all of the little pieces of the stick, including the blob, we calculated what each R cross P would be and then summed them all together. So the key to the conservation idea is that this angular momentum that we start with will equal this angular momentum that we end with. It's just that now we've got more parts that kind of share that angular momentum. So one thing that you would have to do on a problem like this is figure out what your moment of inertia is. This is not just a stick spinning about its middle. This is also the blob spinning around that same pin. So we would have to describe it this way. This is the I for the stick plus the I for the blob. I'm running out of space here. Times, I'll put the omega down there. I'll call this omega final. That's the final angular speed that they would share. And this is probably about as far as I'll go with this. For the stick spinning about its middle, you can look this up on a chart. My textbook has a nice little table of these things. It's 1/2 ml squared. And then for the blob, because all that mass is kind of concentrated at one location, it would just be m times the distance it is from the pin, which is L/2, squared. So that represents the moment of inertia of this whole arrangement here, the stick and the blob combined. And then when we multiply it by the final angular velocity, that represents all of our angular momentum. So this angular momentum expression would be set equal to that angular momentum expression. That's the conservation idea. And then you would just do some algebra to solve for omega or whatever you were asked for in a particular problem. So third case. Now what I've done is I've removed the pin. So this thing is just kind of, imagine a stick just sitting on a table, and it's a nice frictionless table, then we don't have to worry about any external forces from friction. We're still going to hit the blob in the same place on the end, but now you see, because there's no pin, we got nothing to exert this unbalanced or external torque or force on the system. So two things are going to happen. We're going to have the same kind of linear momentum conserved that we had up here in the first one, and we're going to have angular momentum conserved like we did here in the second one. So here's where a lot of students get tripped up on this. They say, wait a minute, I don't see a pin. Is this still going to rotate about the center? It turns out it won't. I'm going to draw a picture here of what's going to happen. It's going to be kind of hard to draw, but it turns out that once these things combine together, when systems are free to rotate like this, they always rotate about the center of mass. And you see where I put the center of mass? It's about halfway between the center of the stick and the center of the blob. And I made the blob and the stick the same mass so that this part would be kind of straightforward. Because we have equal masses for both, the center of mass is exactly halfway in between them. So now two things are going to be happening. This center of mass, that's where we say it has a final velocity. That's v equals the initial velocity divided by 2. It's exactly the same thing we did up here in this first case, but the center of mass here was clearly right at the center of the stick. That's why I drew the vector there. But now we've moved the center of the mass lower, so that part will be going forward. And what else is happening? Well, this whole thing is still spinning around that same location. So this would not be a typical kind of spin like you had up here where it's spinning around the middle. This is sort of an irregular spin where it's as though we had the pin there and we were spinning around that pin while also that pin was moving forward. You can almost think of this in a way like the rolling motion idea where you've got both forward motion as well as spinning motion happening at the same time. So again, I kind of did the linear momentum already because it was pretty trivial. You just end up with half the speed at the end. But that's how fast the center of mass moving. All these other pieces are also spinning around that center of mass. So we would have to do the same kind of thing where we describe the angular momentum beforehand as r cross p. But now the r is not going to be half the length. We have to have, and this is very important, we have to have the same rotation axis when we calculate our initial angular momentum that we're going to use at the end. So we're going to use the center of mass as our rotation axis. That means the r vector is always only going to be L over 4 here. And then the p vector is still m times v initial. So that's what L looks like before the collision. And then L, again, this would be like capital L here for after the collision. We would have to calculate the moment of inertia of the stick with a shifted rotation axis. We cannot use 1/12 ml squared because that only works when you're orbiting around the middle or rotating about the middle. Now we're rotating about a shifted axis. This is the perfect time to use the parallel axis theorem. So here's what I would do. For the stick, I would say, okay, it's 1/12 ml squared. That's if it was spinning around its middle. Plus, parallel axis theorem says, add in another md squared term, where d is how far you shift it. So that's m, and then I've shifted it from the middle down to a quarter of the way down. So that's L over 4 squared. So that part right there is just for the stick. And then I've got to get the blob involved. The blob has a moment of inertia about this axis of m times L over 4 squared just by itself. So now that all together is the moment of inertia of this spinning system. That might be something you need to replay if you didn't catch all that. And then I'm going to squeeze in my omega there because it's I times omega that describes the angular momentum. And I think just because I've gone over 12 minutes here, I'm going to stop because all this would be now would be setting these two expressions equal to each other, solving for something. In a typical problem, you might be given the speed and asked for omega. You might be given omega and asked for the speed. There's different ways to do it. But we've done the key part here, and that is to relate the angular momentum of this blob before it collides with the angular momentum of the entire system after the collision. So a lot going on there, but I think worth looking at all three of those situations to see if you have a problem, which one it looks closest to. So hope this was helpful for you. Thanks for watching.